And there is our speaker. Okay, so our first speaker for today, yeah, you guys can wave at Donavon in the camera. He can see you. So our first speaker for this afternoon may look familiar for those of you who have been here for more than a year. This is Donavon Evans, who was here, as you all know, this summer, but has had to return home to school for this week, which is why he is joining us via Zoom. Donavon has joined us for 2 summers now from San Francisco State University. He's been working with Kyle, and today he'll tell us about their project together. Can LISA resolve black hole binaries in the M87 globular cluster? So go ahead, Donavon, whenever you're ready.
Thank you so much for the introduction, Gwen. Yeah, I wish I could be there in person. I really miss y'all. But I'm also really excited to present my research, mine and Kyle's research today. So let's jump right into it. Yeah. So since the first detection of a binary black hole merger in 2015, the field of gravitational wave astrophysics has transformed our view of the universe. Yeah, so this is a relatively new area of study, with the first observation happening in 2015. And within the last 10 years, one of the most exciting developments has been detecting gravitational waves utilizing LIGO. We can see here on the right, this is a picture of the LIGO Hanford Observatory, and on the left we can see a picture of two like it's basically an artist rendition or a visualization of black hole binary, which is a potential source that LIGO might detect. And so similar to LIGO, LISA will also detect gravitational waves once launched, and I'll get more into that and sort of what that means in just a second. But just for some context, I guess, gravitational waves strain and stretch space-time. So you could think of them as sort of like ripples in space-time. And yeah, let's move on to the next slide. So what is LISA, and why is it important? Well, it stands for the Laser Interferometer Space Antenna, and it's planned to launch in 2037. This will be a space probe that will measure or observe gravitational waves with much shorter frequencies when compared to LIGO's frequency. And so in this figure, we can see the frequency along the x-axis and the sensitivity to gravitational waves along the y. And essentially, these two curves here, I don't know if y'all can see my mouse. Maybe you can, maybe you can't. But on the right side, in kind of like a red curve, is LIGO's sensitivity curve. And then in the blue on the left is LISA's sensitivity curve. And the key thing that I want to point out in this figure is that they are both observing different ranges of frequencies, and thus we'll be observing different sources for gravitational wave emission as well. And I'll get into more of like what exactly LISA and LIGO will be observing and sort of the differences between them. But one of the key things is that LISA will be detecting the inspirals of black hole binaries, so much earlier in their lifetimes, essentially, when compared to LIGO, which more or less observes the mergers of these black hole binary pairs. And so, yeah, one question we had throughout this project was, how do these black hole binaries form? And an answer to that question is through dynamical interactions within star clusters. And so here is just a picture of the Milky Way, and we can see, I don't know if you might be able to see my mouse, but I'm essentially going to trace over. This is the disk of the Milky Way in this sort of blue, the slightish blue, and like pinks and like almost like dark shadows of like black and red. And then in the center, we have the bulge. And then around and throughout the galaxy, we have the halo. And the halo is typically filled with globular clusters. And so these globular clusters or star clusters are essentially, you can think of them as like bundles of stars all within close proximity to one another. And they can be filled with up to like hundreds of thousands to millions of stars, and they can be on the size scale of a few parsecs across. And so, yeah, within the Milky Way, we have observed about 150. And like getting back to our original question at the beginning with M87 and whether or not Lisa can observe any black hole binaries or gravitational wave emission from globular clusters in M87, I just want to point out that, yeah, within M87, there are around 10,000 clusters. So as opposed to like the 150 that are observed within the Milky Way. So exponentially more, basically. And so, yeah, just moving on to sort of the dynamical interactions that take place within these clusters. I want to establish that we can just take this as or I want you all to imagine essentially that this is a star cluster filled with millions of stars and around 1,000 black holes. And throughout the course of its lifetime, the most compact objects, so like black holes, will go through this process called mass segregation, where they will sink to the center of their cluster and then begin to interact and form binary pairs, as seen in this sort of illustration on the right here. And so, yeah, this is, you can kind of think of this as being like similar to how fluids of heavier densities will sink to the bottom of a cup. Yeah, hundreds to millions of years prior to merger in the LIGO band, these stellar black hole binaries may be detectable at millihertz frequencies by detectors like LISA. And because these globular clusters are dense and they contain close proximity of stars and compact objects, they can potentially be good sites for binary formations and thus more mergers. So yeah, to provide some context, there were roughly 100 binary black hole mergers from the simulations that we utilized for this project to make predictions. And speaking of those simulations, we utilized a code called Cluster Monte Carlo, or CMC, which was developed by Kyle along with about 30 or so other collaborators to model the evolution of star clusters and the interactions that take place within them over time. And so the CMC code is essentially a method of solving the gravitational n-body problem, and that problem being sort of like how does a system of n particles, or in our case stars or other compact objects, interacting via the gravitational force evolve over time. And so, yeah, for this project at least, I utilized two catalogs of models and well, to make our predictions. And yeah, those two models, or those two catalogs, I should say, closely represent the Milky Way, and then we scale that one up and wait so that we can make another catalog that would hopefully resemble M87 and sort of the globular clusters that we can expect to see within M87. And so, yeah, just in terms of making predictions, this plot is representative of some of the parameters that change between each of the model star clusters and within the catalog. And yeah, just to go through this figure, along the x-axis we have the virial radius. I also want to point out that each of these points sort of designates a different star cluster within the simulations. And so the virial radius is essentially the approximate size of the cluster. Within the legend, we can see the number of stars for these clusters. And the key that I want to point out in this plot is that as the virial radius decreases and the number of stars increases within a cluster, we can see that the number of binary black hole mergers is significantly larger. And then as we increase that radius, so if we make it much more sparse and have fewer stars, we can see that the number of binary black hole mergers decreases. And so, yeah, the more compact star clusters, they will have a greater number of binary black hole mergers. And yeah, finding sites for these mergers was crucial for identifying potential gravitational wave sources for LISA. And so, given the number of mergers, we asked ourselves how many are lower frequency LISA sources. And so the next step then was to take this catalog of models and estimate the number of black hole binaries in M87 and the Milky Way. And just to point out some of the differences, as I previously mentioned, there's a lot more clusters 10,000 within M87 and 150 within the Milky Way. However, the distance or average distance in the Milky Way's case to these sources is also drastically different. So for M87, it's roughly 16 megaparsecs away. And for the simulations that we used, we had an average distance of about 8 kiloparsecs for the clusters in the Milky Way. And so, yeah, in order to do this, we'll need to take a closer look at gravitational wave signals and sort of what it means to be able to resolve them. And so here, this is a judicial example of an inspiral for two 30 solar mass black holes. And the key to being able to resolve a gravitational wave signal is the height above the LISA noise curve. And so, yeah, just looking at this plot, we can see the frequency along the x-axis and the sensitivity to gravitational waves on the y, which is essentially a measure of the strain for that gravitational wave signal. So how much that gravitational wave is sort of stretching and straining space. And yeah, this example sort of spans and takes this 30 plus 30 solar mass black hole binary and represents the signal at different distances for that same 30 plus 30 solar mass black hole. And so what we can see is that as the distance increases along, or well, just within these different colored curves, the signal becomes a lot harder to resolve. So yeah, like within the Milky Way, there's a much greater height above the LISA noise curve, and thus it would be easier to resolve as opposed to M87, which is much closer to the LISA noise curve. And so we could take this as basically that gravitational wave. The gravitational wave signal is inversely proportional to the distance. And for this project, we determined that an SNR, or signal to noise ratio, greater than 5 would be good enough for a signal to be resolved. Otherwise, yeah, it would just be unresolvable. And so just looking at this next slide, this is a plot of the SNR for all of the M87 LISA sources within our catalog. And yeah, I guess what we were most interested in was just determining how many of them can actually be resolved above an SNR of 5. And in this plot, at least, there were about, oh, well, yeah, for M87, there were about 14,000 potential LISA sources, but 0 of them were resolvable. However, looking at the catalog for the Milky Way, oops, let me get my mouse off there, sorry. Looking at the Milky Way, there were about 300 potential LISA sources, and of those 300, about 3 were resolvable. And so, oh, sorry, are y'all able to, I think my slide is glitching. Hello? Oh, okay, I think I'm good. Sorry about that. I don't know what's happening there. Yeah, but in conclusion, so yeah, based on these catalog of models, we predicted to expect 0 sources that LISA would be able to observe or detect within M87 at an SNR greater than 5, and 3 sources within the Milky Way at an SNR above 5. And yeah, that concludes my slides. Thank you all for listening, and I'll take any questions.
All right, we'll take questions for Donovan. And when you ask the question, please tell him who is speaking since he can't see the room so well. So we'll start with Nicholas.
Hey, Donovan, it's Nick.
Hey, Nick.
Can you see my hand?
Yes, I can. It's good
Nice.
to see you.
Oh, well, wait, you could. Hey,
Hey.
hey, I just wanted to ask. So you only looked at how well Lisa might be able to observe, inspiraling black holes, correct?
Yes.
Okay. And given that you didn't, that you are saying that you only expect 3 sources, in the Milky Way with a great signal to noise ratio, what else do you think might be seen, or can you at least reiterate if you already sort of said what might be seen by Lisa? Because I know LIGO gets many observations. So it seems like you predict that Lisa is going to have so few. So I'm just wondering if there's anything else Lisa might be able to see.
Yeah, definitely. So Lisa will probably be observing other sources just within other nearby galaxies. So at least for this project, we expected 3 sources within the Milky Way, but there would probably also be other sources within other nearby galaxies, either like dwarf galaxies or spiral or large elliptical galaxies that happen to be nearby. But then also, so Lisa will be detecting other sources of gravitational wave emission as well that are like separate from black hole binaries. So maybe like 2 neutron stars as they're inspiraling towards one another, or even like white dwarfs if they're massive enough. But yeah, those are just like a few examples to name some. So there would definitely be other things that Lisa would be detecting. And yeah, that's all I'll say there.
Cool. Thanks a lot.
One more question. Do we have
Yeah.
time for one more question? Down in the front, Lauren.
Okay, I think it was slide like 10 or 11 where you showed what?
It's Lauren who's talking.
Oh, this is Lauren.
Hi, Lauren. I could tell.
Okay. Yeah, so where you showed like I think the like Lisa noise like sensitivity curve that might have been later. Oh yeah, the noise curve. Can you explain a little bit of like why it's sinusoidal but only on one side? Like why, like what parameters of the instrument like lead to that?
Yeah, I used to know this. I actually don't know why anymore. But you're talking about like along this, right? This curve. There is a reason for this bump. I'm just not quite sure what sort of causes it, to be honest with you.
Or on the other side where it like gets like super like high frequency
Oh,
sinusoidal?
this too, you're saying.
Yeah.
Yeah, I'm not too sure about that either, if I'm being honest. But that's a really good question. Yeah.
All right, let's thank Donovan again.